Okay. Yeah, so, and the reason this is an issue, I'll see in a bit. I'm gonna stop, like, getting ahead of myself. So yeah, so there's also gonna be some frequency offset, and there's also always gonna be some phase offset, because, like, even if you try to start the, if you try to turn on the transmitter and the receiver at exactly the same time, like, it's basically impossible, because it's, like, a very, you need, like, a lot of precision for that. And so when it comes to symbol synchronization, there's, like, two different things that we, I guess two different questions that we need to answer. Oh wait, hold on, maybe I'll write it on here. The first is just, oh, I see what happened. The first is just what is the symbol phase, which relates to the second bullet point, because there's always going to be some phase offset that we don't know. And then, my bad. What is the symbol phase? And the second, based on, wait, okay. These are not super organized, my apologies. But from this second question, or this first bullet point, the question that we need to answer is, what is the symbol frequency? Yeah, and then, so, the thing that I'll note is that for symbol frequency, like, we just kind of, in our code, we just have our, like, oh, SPS equals sampling frequency over symbol rate. But the thing is, the transmitter, well, first of all, the transmitter isn't perfect, so its SPS isn't going to be exactly, for example, 80. And the receiver, which we just talked about, the FS for the receiver, the sampling frequency for the receiver, is not going to be exactly equal to the sampling frequency for the transmitter. Yeah. Yeah, so to give a bit more, like, of a to give you a bit more of a concrete idea of what we're actually talking about here, is that in our current simulation, we just kind of start sampling at the beginning of the signal, and this works for us because there's no phase offset, because we're working in the idealized MATLAB simulation world. And we also just downsample, or let me write this down, yeah. Start sampling. And then we also just downsample by doing we just take every SPS sample. And that works for us because in our simulation, the SPS is this exact number that both the transmitter and the receiver know. Yeah, and then, so, like, the implicit assumption that we've been making here is that the symbol phase is 0, and a bit more organized. So if we start sampling at the beginning, the assumption there is that the symbol phase is 0, and if we downsample by doing 1 colon SPS colon n, the assumption there is that the symbol frequency is precisely SPS. And neither of these are true, because in real life, what you would really see is, assuming that all the carrier recovery has gone well, which indicates that the blue the two blue signals like line up perfectly. The clocks are not synced perfectly. So like it's a little bit tricky to see, but if you like kind of draw a line with your eyes, the transmitter, like the ideal places to sample are here, but the receiver clock is slightly delayed, so we end up sampling at slightly later points, which isn't a big issue right now because, like, for example, these two symbols are 1. These two symbols will also be interpreted as a 1 because they're still greater than 0. But the thing is, we get kind of anxious when it comes to symbols, say like over here, because they're getting closer to 0, and we know that once we add noise into our system, it's really easy for small symbols to flip to the wrong one. Does that make sense so far? Cool. So, oh yeah, and then I'll also mention that the ideal, or okay, well I guess I'll ask you, like what's the ideal place to sample a signal for a given symbol period? Like if we highlight this portion of the pulse, let's say that this, maybe it's better to delineate it like this, that this section of our signal corresponds to this symbol that is a 1. Like, where's the best place to sample within this range? Just the middle, yeah. Cool.
Is that obvious?
Yeah. Yeah, and then, okay, this is a side note, but I think it's kind of cool. Like, and here's where you kind of see the relation between the pulse shaping filter and the amount of leeway that we have when it comes to symbol synchronization, because you can imagine if we didn't have a band limited channel and we could just do, it's gonna get busy, okay. And we could just use a rect function as our pulse. Then it's like, oh, really anywhere here is like a quote unquote ideal place to sample. Or if we use a root raised cosine where the beta is smaller or larger, I forget which way it goes, then the roll off would be steeper. So you have much less margin for where you can sample. Because then if you sample like, oh, just a little bit apart, you've already lost so much magnitude for your sample. Cool? Cool, huh? Is that cool, y'all? It's week 5, I understand. Okay. So, yeah, and then the reason I brought up this idea behind, I'm not gonna get ahead of myself. We're gonna follow the plan. Okay. And then, yeah, we kind of already answered this question, but if we need to sync both the frequency and phase for the symbols, both the symbol frequency and the symbol phase, does it suffice just to sync the symbol frequency? Does that question make sense? Okay, if you need to sync both the symbol frequency, which is like getting the SPS of the transmitter to equal the SPS of the receiver, And you need to sync the symbol phase, which means that like the first symbol 1 damn, I don't have a good notation for this, but the symbol 1 of the transmitter, the time where symbol 1 at the transmitter exists is the same time where symbol 2 of the receiver exists. Anyway, okay, so no, okay, yeah. Does it suffice to sync just the phase? Yes. And this is the same logic that we use for the Costas loop. Very convenient for us. Cool. And then, okay. Okay. And then, I want to see if I can do the thing where we lead you to the algorithm. But I think for sake of time, I'm just gonna continue talking. So when it comes to the actual algorithm, the thing is that the only aspect that we really have for the true samples per samples per symbol and the symbol phase, it turns out that like the only really like piece of information that we have on like where we should be sampling is something that we'll refer to as zero crossings. So if you notice, well, zero crossings are just where our signal crosses zero. So like here, here, and here, for example. And they happen, of course, whenever our symbol transitions from a 1 to a -1 or from a -1 to a +1. And what you'll notice is that if our symbol period is t, so the time here will be t, just kidding. The time here will be t. Time here will be 2t. Nope, just kidding. Did I mess this up? Hold on. So the idea is that the zero crossings occur, like if a zero crossing occurs at sample n, then we know that a symbol occurs at n plus or minus SPS over 2, because the zero crossings occur right in the middle of when we transition from one symbol pulse to the next. I'm trying to think of why this one doesn't look. Oh, I think what happened is that so if you'll notice the baseband transmitted signal, this first blue plot, the shape of it looks slightly different from the baseband signal for the received plot, and the reason for that is, well, there's several reasons, but it's just like distortions that occur as a result of the Roux cosine and the low pass filter and stuff. But you can see more clearly in the transmitted baseband signal that the the zero crossing occurs at n plus or minus SPS over 2, which honestly kind of seems to defeat the purpose of using zero crossings, but this algorithm does work. So I will get back to you on that. Okay. And then, yeah, so we know that if you take the modulus, so like, okay, so say we have some SPS, some guess for the SPS, and we're like, oh, like, say that we want the SPS to be, like, okay, basically the idea is that we know that whatever SPS we have, our zero crossing should always occur at, like, I have in my notes, like the modulus number of samples that have passed since the last zero crossing should equal 0, and if it doesn't, we have an issue. And so that is our error function that we will use to tune a PID controller to get the correct SPS. Cool.
Is the modulus like just the number of symbols, or the number of bits, rather?
No. Let me try to explain this better. So, like, we know that, well, for example, we know that a zero crossing isn't going to happen at every SPS because, like, we don't always want to transmit +1s or -1s or -1s to +1s. So what we want to do is just take the modulus of the SPS that we think have passed, and that should equal 0. I will upload notes that go into more
detail. It's
detail.
like the base, like which for the mod, right?
Yeah. Well, so okay. So the base is the SPS. So like, let me write this out. So our error function is going to be the number of samples between zero crossings. Modulo SPS. And this function, or this value should be 0. Now I will say, the function that we have just right now, will make our error always positive, and we know that if we want to put a PID controller on this, it's just going to blow up. So what we do is that we center this function around, we center this function around 0. So what we're going to do, there is a way to do like, error can be, there is a way to center this function around 0, but we're actually going to take a different approach to like finding the correct SPS by actually looking at the SPS in terms of frequency, which is similar to what we did in the Crassus loop. Yeah, this is just what I said in words. But yeah, so to give a general idea of what we're going to do is that we know that every sample that we take, like, it takes, okay. So I'll call, no, okay. Wait, hold on. Okay, I have a feeling that I might explain this wrong. My apologies. So I'm just going to give the high-level overview of this. Is that it takes some number of samples, we'll call it M, to return to the same point. So, like, you can think of selecting samples as going around in a circle, because you're always picking samples in a periodic function. So, is it for each symbol? Okay, wait, so if you have, okay, so the phase, the phase of this, like, rotating function as a, over n samples, okay. I think I'm just gonna say, like, we know that since there's a zero crossing at, like, right in the middle of the like the transition from one symbol pulse to the next, we know that if we're sampling in the correct spot, say we're sampling whenever the phase equals 0, then we know that we should expect a zero crossing at pi, because that's the period over 2. So what we can do is basically, like, adjust using a control loop where our sampled value lies on this phase plot versus where we see the zero crossing occur. That's the general gist of it. And we have this, like, that is SPS. Okay, I'm gonna write out, like, the general algorithm for this. Hopefully it makes more sense. So, like, what we're gonna do is go through all the samples, and we're gonna keep track of the, like, phase of the phase that we think is the sample that we're getting. So phase at n equals phase at n minus 1 plus 2 pi over SPS. Because if you think about it, like, each one of these, because if SPS equals 80, then you can think of each additional sample as being a slice of this phase plot that has, like, 1 over 80 times 2 pi. And then if the phase at n is basically within some margin of pi, so say, like, maybe this will be our margin, because it's never perfectly going to be at pi, then we're going to it's negative, Oh, okay. Sorry. Okay. If the phase at the current sample value lies within the. Oh, okay. Sorry. If the current phase lies within, like, say it's maybe up here, so getting close to the margin, and the previous phase, well, I guess that one should be the previous phase. Okay, if the previous phase was just above pi, and the current phase is just is just below pi, we know that a zero crossing. Nope. Do we know that a zero? No, the zero crossing occurs. Okay, there. Okay. I have record samples here in my notes. Okay, I'm gonna have to think back on why that makes sense. But if the current phase is what's the name for it? And the previous phase. Then we record samples. But then, if a zero crossing occurs, okay. Okay, when a zero crossing occurs, we know that the error, oh, I see, sorry, okay. We said that we're sampling at pi. This makes sense, okay. Yeah, so if we've just crossed pi, then we know that a sample has occurred because we're expecting that the zero crossings occur at 0. And that just is more convenient when we're working with error because it's like centered at 0. And then our new SPS guess is going to be updated based on our PI controller. Okay, that's the general idea. Does the general idea make sense?
Kind of.
Kind of.
At least
Okay.
the last one.
Okay. Good. That's all I can ask for.
Just one question. Can you restate the margin again, or are you doing one here?
The margin is just saying like, oh, we want to know that that we have just crossed the threshold where we would expect a symbol or a sample that we want to exist.
So basically, it's the margin defined by the user.
Yeah.
Okay.
Yeah. It honestly, I'll probably just give y'all a range and you can see which works best for your system. But it'll be like fairly small because we want to make sure that we get the 2 samples that are closest to having crossed pi, because we don't like if there's a sample here and a sample here, like we don't want to pick those. Okay. Cool. Okay. That's all I have for the symbol synchronization portion. Before getting into the frame synchronization portion, we have an icebreaker. I'm just gonna make Zaire answer your name, pronouns, year, and hometown,
Sure.
and what one thing you're looking forward
Well,
to this weekend.
hopefully everyone knows my name. Pronouns. He, him. Year I'm a junior. Hometown. I'm familiar with Northridge, San Fernando Valley, kind of right in the middle. If you know where Seaside is, it's like right there. One thing I'm looking forward to this weekend, honestly, there's nothing. There's nothing good next week, so this weekend's gonna suck because midterm season. But I am looking forward to no rain, I guess.
Oh yeah,
no
that's a good
rain.
one.
Let's go with that. No rain. Don't ruin my hope. let's. Yeah, hopefully no rain.
Yeah,
And midterm prep.
yeah. Good.
Fun times.
Good. Okay. Part 2 of our lecture is frame synchronization. So just to give more context for what this problem is, suppose that the transmitter sends the letter S in ASCII, which is this 8-bit packet of bits. And suppose that the receiver then demodulates correctly using our handy-dandy Costas loop, and we downsample correctly using our symbol synchronization zero-crossing algorithm thingy. And the question is, can we assume that the first bit that the receiver receives corresponds to the first bit that we send? No. Yeah. Because the thing is, the receiver like doesn't know what is what. The receiver is always listening, and even though the transmitter only sent the letter S right here, before it sent the letter S and after it sent the letter, like, even though the transmitter wasn't sending anything, the receiver is just picking up noise. And it really has, as it is right now, the receiver has no way of distinguishing when a packet begins or ends, or just like delineating what this string of bits, like how to structure it. Yep. Things that I just said. So detecting receiver's always listening. How does it know when a packet starts and ends? So detecting the end of a packet is actually pretty easy. So we just restrict our packets to a known length. So there's going to be a set number of symbols being sent in each package. Really, the trick here is figuring out the start of each packet, because it's like you want to retain the time domain order. And we don't want to and like we want to, I guess, interpret packets as a whole. So the way that so to kind of like break down this problem a bit more, as in how to detect the start of each packet, of each data packet, is that we're going to have the transmitter start each data packet with a certain string of bits. This is called a packet header. And the receiver knows this a priori, knows it before the fact. So it can be on the lookout for this packet header, and when it detects this packet header, it knows that the subsequent however many bits of that it receives form a data packet. So because it knows the size of the data packet. So what we need to figure out is, one, how is our receiver going to be able to detect the packet header, and two, what string of bits should we use as our packet header? And we, because it's like, we want to know, I guess one way that you could do it is just like have an if statement, but we want to be like a little bit smarter about it. So the way that we're gonna do that is this mathematical operation that detects how similar two different signals are, and this is called cross correlation. Anyone heard of cross correlation? Okay.
Brooks bringing it up in class.
Okay, we also talked about it in 132A. But cross-correlation is just a math operation that's similar to convolution in that you have two signals and you do this multiply and sum operation, but there's no flipping. Oh, I should write this down. And because of this, like, multiply and sum at each time, but no flipping, cross-correlation is also often referred to as the sliding dot product, where a dot product is the, like, thing from linear algebra that we know, like x1 times y1 plus x2 times y2. Etc. If you have some vectors. And then the third thing that I want to mention about cross-correlation is that it's commonly used for searching a long signal. For a shorter known feature, where a feature is basically just like a shorter signal. And importantly, by using the cross-correlation, you can see, by cross-correlating with like the correct sequence of bits, you can also see where this shorter known feature lines up with or like shows up in the longer signal. So I have this diagram of like every operation that you would do. But basically, can you read that? Oh, you can. Okay. For example, if we have some sequence of data, this is our packet header, and we're just gonna we're just gonna like keep shifting our our second signal throughout the entire first signal, and what you'll see is that there's gonna be a peak at where the two signals kind of line up. I don't include the graph in here, which is my bad, but I have a graph for, I think I have a graph for the next one. Anyway, so that's kind of the idea of using cross-correlation. And the next question was, what string of bits should we use as our packet header? And this question is very tied to the way that the receiver detects the packet header via cross-correlation. Because we want to choose a string of bits such that when you cross-correlate it with any incoming signal, the output of that cross-correlation is going to show a clear peak at wherever that packet header occurs in the received signal. So there's a lot of like cool information theory topics on what the optimal packet header is to use. That's a topic called Barker codes, which you can look into if you're interested in. The packet header that we use isn't actually a Barker code, and it works. I believe that the reason why we picked it is because someone on like DSP Stack Exchange said it was good, but it works. It may not necessarily be optimal,
Well enough.
but that's something that we're gonna explore in software R&D. Woohoo! Join software R&D. Yeah, and then I guess like another intuition for cross correlation is it's like whenever the two symbols match, you're like integrating their energy at that point. So like you get a peak whenever there's a lot of matching. Flavio explains this better than I can. Okay. Yeah. So I guess to like give a bit more of a concrete example, actually, I'm going to save that slide for another time. But the other thing that frame synchronization fixes for us is our issue with the Costas loop, which was called false lock. Where, well, it fixes one of the false lock issues, where sometimes if you have a one symbol, like if you have a symbol that should be a 1 and it'll land where the 1 is, and you have a symbol that should be a -1 and it lands where the -1 is, our Costas loop doesn't actually know if it doesn't actually know like which symbols are +1 or -1. So you could very well, and some of you have seen this, get a 100% bit error. If your Costas loop locks with the 180-degree phase shift, so like all your -1s end up at +1 and all your +1s end up at -1. And the reason for this is because the error function that we use for the Costas loop just looks at whether the quadrature component, or whether the in phase times quadrature component equals, we just want the in phase times quadrature component to be 0. And I mentioned this to some of you, like the other thing that can happen with the Costas loop is that we can lock on here. That issue hasn't been something that we've seen occur as often, so we can also address that in software R&D. But yeah, so the thing is with packet headers, what we can do is if we detect, so like the cool thing about correlation is that you'll get a very strong positive peak whenever the I'm trying to figure out that. You'll get a very strong positive peak whenever your signal like matches your other signal, but you'll also get a very strong negative peak if your signals are exactly opposed. So if we cross correlate and we see a very strong negative peak, then we know that we've received this packet header, except that every bit is reversed. So then what we can do in our code is just have this like, oh, if the cross correlation is super negative, then just flip all the bits that we receive. So that's like very convenient. And then this is another what we'll see with cross correlation. So, oh, that's 3 sequence repetitions. Yeah, see, because there's not quite sequence repetitions. But anyway, also like a very convenient aspect of this packet header that we use is that when you cross correlate it with our received signal, you'll see 3 large peaks, which just like makes it more resistant to noise. Because what you'll also see in the module is that like if you have noise, then noise can also kind of like make the cross correlation look like it's there, but it's not actually. Yeah, that was a very high level overview of how we do frame synchronization with packet headers and cross correlation. Any high level questions? Kind of makes sense. The module will be clear. Thank you for your patience. And then I have these additional resources, which I always recommend. But yeah, that is all for this lecture. Do you think of any other announcements you wanted to give?
I think so. That's it.
Okay. Thanks for coming out on a rainy Wednesday evening.
How do we get back?
Tell me how you get back.
Get back very wet and soaked.
Oh, you don't have an umbrella?
No.
It's like I don't need. I have my hood, and that's good enough.
Yeah.
Yeah.
I don't even have a hood.
Okay. Yeah.
Alright.
Better run.
No, you get more wet if you. This is Mythbusters proved this. If you
Yeah,
run,
they
you get
did
more
prove
wet.
this.
That's true. For sure. There's an optimal speed, isn't there?
What?
Isn't there an optimal speed?
Yeah, that's such an engineering thing to do.
What if you just run backwards?
Find the optimal speed to walk.
I don't think
If
that
you walk
works.
too
I
slow,
think
get
if you run
stuck.
backwards,
When you run
Yeah,
too fast,
I
you
think
get
it's
stuck,
fine.
So there's
Yeah.
optimal speed.
Then you're running
There's
into less
gotta be a
water.
minimum.
Yeah.